gives me exceptional pleasure to introduce Professor Claude Cohen-Tannoudji of the Collège de France for this special seminar that we're having today in honor of his having won the Lilienfield Prize of the American Physical Society. The Lilienfield Prize is awarded to a scientist of exceptional distinction in science and also in the ability to communicate science to others. And I won't labor the appropriateness of that prize, since I think that will become self-evident during the course of his talk. I would like to talk a little bit about Claude's background, because we've been friends for many years, and I have known and appreciated his work for many years and admired it, and admired the tradition from which it comes. It is the tradition of Alfred Kastler, who essentially played the pivotal role in reconstructing science in France after World War II, who pursued a life of interest in the interactions of atoms with radiation and set a style for teaching and for lecturing, which has influenced his school, the École Normale Supérieure, and who established a tradition of which Claude Cohen-Tannoudji is the inheritor. He has passed on this tradition. Many of you have heard his students speak, Serge Haroche for one. Alain Aspect, who technically was not a student but worked very closely with Claude in recent years, is another exemplar of that tradition. Claude's work has been concerned with the interactions of atoms with radiation from his graduate student days, when he attacked the problem of light shifts, which were then a very mysterious effect, which were confusing people involved with precise optical pumping experiments. And out of those studies eventually came his theory of the dressed atom theory. It really sounds so much nicer in French, the atomes habillés. But in English, it's the dressed atom theory. And this is a picture which is now widely used to discuss phenomena of atoms and radiation and many other phenomena too. So this whole new way of looking at quantum systems was developed by Claude. In addition, many of you are probably familiar with his name through his books, his famous textbook on quantum mechanics, and more recently, 2 monographs on quantum optics and the interactions of atoms with the radiation field, the latest one of which has just been published in English, I am sure going to be the standard works in these areas in the future. Claude is at the École Normale Supérieure, but actually he's a professor at the Collège de France, and this is all too complicated to explain, but I do want to point out the uniqueness of being a professor at the Collège de France, because it is the most demanding institution in the world for a teacher. It is a demanding institution because there are no examinations that it gives, no grades that it gives, no degrees that it gives, and no students that it has. Okay? Now, you might think this makes it all very easy, but it isn't. On the contrary, it makes it very demanding, because the lectures at the Collège de France are open to the public, and people come simply because they want to learn and not because they have to. And if you're not a good teacher, you lose your audience. And this puts a tremendous strain on the teacher, I think. At least I couldn't conceive of trying to really attract my audience willingly week after week, and in fact, year after year. Because there's another rule there that very few of us would put up with, namely, you do not repeat your lectures. Each year's sequence is a new series of lectures. So it is, for these reasons, the most demanding institution in the world for teaching. And Claude is one of the great teachers of the Collège de France. His lectures there are packed. People come from wide areas around to hear him, and without saying more, I think you will see why. Claude.
Thank you very much for your introduction. Before starting, I would like to tell you how much I'm happy to be here again in MIT, because I was here in '76, spent some sabbatical stay in MIT and Harvard, and it's for me a very great pleasure to be here for a few days, and would like to express my warmest thanks for Dan, who immediately after the announcement of the Lilienfield Prize invited me to give one of these lectures here at MIT. And thank you very much, Dan. My lecture will deal with photon-atom interaction, which, as you know, play an essential role in atomic physics. And they can be considered from two different points of view. First, they provide information of atoms. They can be considered as a source of information, because by looking at the light which is absorbed or emitted by atoms, you can get information on the structure, on energy levels. That's the whole field of spectroscopy. There is a second point of view, which is that this interaction can be used for acting on atoms and for controlling their degrees of freedom. In the 50s, 60s, as Dan mentioned to you, in the group of Alfred Kastler and Jean Brossel in Paris, there have been a lot of experiments where exchange of angular momentum between atoms and photons were used to control the internal degrees of freedom of an atom. That's the field of optical pumping. Now, more recently, during the last 10 years, a new field is exploding, which is called laser cooling and trapping, and one uses laser light to control the external degrees of freedom of atoms, the velocity and the position. And what I would like to focus on in my lecture is this second point of view. I'd like to show you how it's possible to manipulate atoms with photons, and I would like also to show you that there is a certain continuity between these two lines, and how optical pumping turns out to be a very important aspect of laser cooling and trapping. The outline of my lecture will be the following. I will first give you a few examples of processes where one uses photon-atom interaction for controlling the polarization, the energies, the velocity, or the position of an atom. All these effects use the basic conservation laws of energy, angular momentum, linear momentum, and are just simple illustration of quantum mechanics. Then in the second part, I will describe more recent development in this field, which allowed us to cool atoms to the micro-Kelvin range and to get what we call now ultra-cold atoms. And I will describe mainly two effects, two cooling mechanisms, the so-called Sisyphus cooling mechanism and the velocity selective coherent population trapping, which result from an interplay between optical pumping, light shift, and radiative forces. And finally, in the last part of my lecture, I would like to discuss a few possible applications of these cold atoms. And I've chosen two applications. First, cesium atomic clocks using Zacharias atomic fountain. I'm particularly happy to speak of that here because Zacharias was trying to do such a scheme here some time ago. And the second example will be a gravitational cavity for neutral atoms. So let me start with a few processes. And the first one will be optical pumping, which is a transfer of angular momentum from polarized photons to atoms. As you know, the momentum, angular momentum, which is carried by photons, depends on the polarization of light. If you take a sigma plus light propagating along the z direction, the photon of this associated with this light beam carry an angular momentum plus h bar with respect to this axis. Suppose that this beam is resonant for an ensemble of atoms which is contained in a cell. And suppose, to simplify, and that corresponds to actual experiment, that the atomic transition connects a ground state with the angular momentum 1/2 to an excited state with an angular momentum 1/2. So we have two Zeeman sublevels in the lower state and two Zeeman sublevels in the upper state. The sigma plus light can excite only the transition between G minus 1/2 and to E plus 1/2, because when the atom goes from this state to this state, it gains a momentum, an angular momentum delta m equals plus 1. It goes from m equals minus 1/2 to m equals plus 1/2. And this angular momentum is provided by the absorbed photon, sigma plus photon. So only this transition is excited by the atom. Then, when the atom is in excited state, after a short time, which is the lifetime of the excited state, it falls back to the ground state, either here, in which case it returns to the initial state, or by emitting a pi photon, delta m equals 0, in which case it falls back in G plus 1/2, where it remains trapped, because there is no sigma plus transition starting from G plus 1/2. So at the end of such a cycle, atoms have been pumped from here to here via E plus 1/2. and they have gained, on the average, an angular momentum, delta m equals +1. And if the relaxation time due to the collision of atoms on the walls is long enough, it's very easy to put nearly 100% of the atom in this state. So that optical pumping mechanism is a very efficient method for polarizing atoms with 100% efficiency. Now, I'd like to emphasize another important point, is that such a scheme is also a very sensitive detection method, because as you can see on this picture, only atoms in G-1/2 can absorb sigma plus photon. So by measuring the absorption of the light beam or the amount of emitted light, you have a signal which is proportional to the population of this level. Now, if all atoms are accumulated here, the vapor is transparent. Now, you can, if you apply a static magnetic field along the z-axis, introduce a Zeeman splitting between these two states, and apply a resonant radiofrequency field which induces radiofrequency transition between the two Zeeman sublevels. Usually, magnetic resonance is detected by the absorption of the RF photon. But you see here that any RF transition bringing the atom from G+1/2 to G-1/2 can be detected not on the RF photon, but on the subsequent absorption of an optical photon from G-1/2 to E+1/2. So we have an enormous amplification factor because it's much easier to detect an optical photon than a radiofrequency photon. This is why such methods have provided the possibility to study very dilute substances. Now, you could see now, ask two questions. I have taken here a resonant light beam. What happens if the light beam is slightly off resonance? I've taken the light beam along the magnetic field. What happens if the magnetic field is no longer parallel but perpendicular to the magnetic field? I would like to study now these two cases and to show you that interesting things have happened. First, let me consider what happens if the light beam is perpendicular to the magnetic field. It's called transverse optical pumping. You see that if the light beam was alone, atoms would be optically pumped in the plus x direction, and they will be prepared in a state which is the eigenvector of gx, the component of the angular momentum along the x-axis, which is itself this linear superposition of G+1/2 along z and G-1/2 along z. But that's not the whole story, because you have now competition between optical pumping, which prepares atoms in this state, and the Larmor precession around the magnetic field, which makes this spin, this magnetic moment, precessing around OZ with a Larmor frequency proportional to B0, omega L, Larmor frequency. So you have a competition between two processes with different symmetries. So if you want, for a given value of the magnetic field, determine what is the steady state orientation in the ground state, you have to sum the contributions of all atoms which have been optically pumped in the past of t, that is to say for t minus tau with tau positive, and which at time t has not yet been disoriented by collision or by absorption, which have survived relaxation processes. So what you have to do in the x or y plane is to consider atoms which have been just pumped at time t equals, at tau equals 0 at time t, and which are oriented along x with a magnitude 1, let's just take 1, and then atoms which have been pumped a time tau before, which are rotated by an angle omega L tau, and which have survived relaxation process, so their contribution has been decreased by e to the minus tau over tau g, where tau g is the relaxation time of the ground state. And then you have to integrate over tau from 0 to infinity. And you see that in this case, it's clear that you have two limiting cases. The case where during the relaxation time, tau g, the rotation, the Larmor rotation is very small, in which case you have to make the vectorial sum of vectors which are nearly parallel. So you get a large value of gx and the small value of gy, which is roughly omega L tau g. And the second case, where omega L tau g is much larger than 1, in which case all the vectors you have to sum are nearly isotropically distributed, in which case gx and gy is equal to 0. And you see that the critical value of the field is a field such that omega L tau g is of the order of 1 radian. So if you plot the steady state value of Gx and Gy versus omega L, you see that you have an absorption shape for Gx, a dispersion shape for Gy, and the width of these two curves is delta omega L, where delta omega L is such that the corresponding delta B naught, delta omega L is such that delta omega L tau is of the order of 1. If you take a cell with a very good relaxation time, let us say 1 second, and if you take a paramagnetic atom in the ground state, 1 megahertz per Gauss, this width in magnetic field corresponds only to 10 to the minus 6 Gauss. So you see that this is nothing but the Handler effect, but Handler effect in ground state, where because the lifetime is much longer than in excited state, the Handler resonance curves are extremely narrow. And actually, we observed such effects a long time ago on 87 rubidium with Jacques Duporoc and Serge Haroche. And let me give you here an example of Handler curve in the ground state of 87 rubidium. You see that the width is 1 microgauss. The signal to noise is about 10 to the 4. So if you put here, if you put yourself here and you vary the field, you see that you can detect very easily a fraction of nanogauss. So that's a very sensitive magnetometer. I think it's a sensitivity which is comparable to the squid. And which uses at that time, that was using just ordinary lamps. And actually, this magnetometer was sensitive enough to detect the static field produced by a gas of oriented nuclei. One takes a cell of 10 centimeter diameter filled with optically oriented helium-3 nuclei with a density of 5×10 to the 15 per centimeter cube in 100 centimeter cube volume. And we put the rubidium cell nearby, and we make the Handler resonances on this cell, and we detect the field, the macroscopic field produced by this oriented nuclei. Nuclei has very small magnetic moment at a macroscopic distance of 10 centimeter. And to make things with more fun, we apply a very small magnetic field to the helium nuclei in order to have them precessing with a Larmor period of a few minutes. And that's the field we detect on the rubidium cell. And you see a very good Larmor detection of the Larmor frequency 3 hours later and 11 hours later, and we still see the nuclei rotating. Actually, this experiment is done in a magnetic shield, and we tried to apply it to see the magnetic field produced by Hertz, but the magnetic shield was too small for introducing even a baby in the shield. But now with squid, it's currently used to measure the magnetic field produced by the brain or by the Earth. Before leaving this experiment, I've described it simply with magnetic moment, Larmor precession. We can give a more sophisticated description, not for complicating things, but because I think it provides the basis for understanding a more modern experiment where we have cooling atoms below the recoil, and which is called coherent population trapping. Because suppose that you have zero field. If you have zero field, you can take any quantization axis. Now, if you have zero field, you know that the atoms are optically pumped in the direction of the light beam, and they no longer absorb light. How can you understand that? If you take the beam along the x-axis, and if you take as a quantization axis the z-axis. A sigma plus beam along the x-axis has a polarization, which is a linear superposition of the sigma plus, sigma minus, and pi polarization along the z-axis. So sigma plus along x is within a constant factor, pi over z along z plus 1 over square root sigma plus along z plus 1 over square root of 2 sigma minus along z. Now, optical pumping prepares atoms in the g plus 1/2 x state, the eigenstate of gx with eigenvalue plus h bar over 2, which is the linear superposition of g minus 1/2 z and g plus 1/2 z. So atoms are in this state, and from these two states, you have pi, sigma plus, sigma minus transition. But what is nice here is you have a linear superposition of these two states, And the polarization of the field is a linear superposition of sigma plus, pi, and sigma minus. And if you take this superposition, the amplitude for absorbing a sigma plus photon is the amplitude to be in G minus 1/2, which is 1 over square root of 2, times the amplitude for the beam to be sigma plus, which is 1 over square root of 2. And the amplitude of absorbing a pi photon is the amplitude to be in G plus 1/2, which is 1 over square root of 2. And the amplitude for the photon to be pi, which is pi. And if you multiply these two amplitudes by the Clebsch-Gordon coefficient of this transition, you easily find that the absorption for sigma plus and the absorption for pi interfere exactly destructively. So the atoms are in a linear superposition of two states. The photon is a linear superposition of two polarizations, and the two absorption amplitudes from here and from here to here interfere destructively. And they interfere also destructively from here and from here to this state e to the minus 1/2. What? Pi is a polarization which is linear and parallel to the z-axis. A pi polarization with respect to the z-axis is a linear polarization parallel to the z-axis. There are three basic polarizations for photons, which are sigma plus, like that, sigma minus, like that, if I take the z-axis, and pi, like that, corresponding to the three possible values of the angular momentum of a photon, which is g equal 1.
I thought there were only two ellipses.
There are two, if you take as a quantization axis, the momentum of the photon. But a pi photon is a photon which propagates in the x or y plane, and which has a polarization which is linear and parallel to the z-axis.
But aren't there still only two states?
A pi polarization is a linear superposition of sigma plus and sigma minus. But it's called usually in atomic physics, it's a transition delta m equals 0, it's called a pi polarization. Now, another important thing here is that in zero magnetic field, the two states, G plus 1/2 and G minus 1/2, have the same energy. So if the atom is in such a state, it remains there indefinitely because this state does not evolve. Now, if you put a small magnetic field, so if you have the optical pumping along X, and if you put a small magnetic field along Z, the state G plus 1/2 along the X-axis is still a non-absorbing state, a non-coupled state. But once the atom has been put here, this state is no longer stationary because the phase factor of appearing in the time evolution for G minus 1/2 and G plus 1/2 are not the same. This means that the state evolves. The state G minus 1/2 is G plus 1/2 is coupled to the state G minus 1/2, which can absorb light. So I think the general idea we can keep from this experiment is that there are situations where atoms can be prepared in states which are linear superposition and for which there exists several absorption amplitudes which interfere destructively. That's a very interesting quantum interference effect. Now, two situations then can appear. If the state is stationary, if the states which are linearly combined have all the same energy, an atom which is here remains there indefinitely. So all atoms will be optically pumped in such a state which no longer absorb light, and the fluorescence stops. But if you add a perturbation such that the states which are linearly superposed are no longer the same energy, then the state is not stationary, is coupled to other states which absorb light, and the fluorescence reappears. That's the main scheme of what is called coherent population trapping. And we will see another application of this effect later on. Let me now give you a second example. What happens if the light beam, which makes the optical pumping, which is now, I come back to longitudinal pumping, what happens when it is non-resonant? So I would like to show you now that it's possible to displace atomic energy levels by quasi-resonant photons. That's light shift, or still called AC Stark shift. And I would like to give you an interpretation of this effect in terms of dress state. Let me first consider the uncoupled state of the atom plus photon system. for example, this state is Gn, atom in the ground state G in presence of n photons. En minus 1, this state is the atom in the excited state E in presence of n minus 1 photon. If the laser frequency omega L is equal to the atomic frequency omega A, these two states would be degenerate. If we are off resonance, slightly off resonance, the two states are not degenerate, and the splitting between them is just H bar delta, where delta is equal to omega L minus omega A. Now, the atom in G can absorb one photon and jump into E. That means that the laser atom interaction Hamiltonian, VEL, has a non-zero matrix element between Gn and En minus 1. And this matrix element is nothing but H bar omega 1 over 2, where omega 1 is the so-called Rabi frequency, which is well known in magnetic resonance. So these two states are coupled, and it's well known in quantum mechanics that when two states are coupled, they repel each other. This state is shifted down, this state is shifted up, and if we are in the perturbative regime where the coupling H bar omega 1 over 2 is small compared to the splitting H bar delta, we get a shift which is omega 1 squared divided by 4 delta, and that's just the light shift. So you see that the light shift is proportional to the light intensity because the square of the Rabi frequency is proportional to the light intensity. Its sign depends on the detuning because it's 1 over delta. If omega L is larger than omega A, delta prime is positive. If omega L is equal to omega A, delta prime is negative. You could ask what happens if omega L is equal to omega A. Now we have two degenerate states. When you introduce a coupling, you get a doublet, a symmetric and antisymmetric linear combination, and that also is well known in atomic physics. There's the Outler-Towns splitting of spectral lines. And finally, of course, it depends on the light polarization. Actually, light shifts were observed about 30 years ago. This was the subject of my thesis. These light shifts were called lamp shifts by Alfred Kastler because they were produced by the light coming from a lamp. That was a play word for comparing them with lamp shift. And actually, the experiment was done on a 1/2 to 1/2 transition on mercury, like that. And the experiment was done in 2 steps. In the first step, one make optical pumping, one measure very accurately the transition frequency between G minus 1/2 and G plus 1/2. That's the green curve. And then in the second step, one adds a second beam of light, a second light beam, consisting of light coming from a different isotope of mercury. So it's shifted in frequency. And this light beam can be polarized either sigma minus or sigma plus. And you see immediately on this picture that if it is sigma plus, only G minus 1/2 is shifted. If it is sigma minus, only G plus 1/2 is shifted. So you see that in one case, you increase the splitting between the two levels. In the other case, you decrease the splitting between the two levels. And this is what is observed experimentally. The magnetic resonance curve is shifted in opposite direction, depending the polarization of the light is sigma plus or sigma minus. Now, I come to a third example, which is the transfer of linear momentum from photons to atoms. Suppose that you have a laser beam, a laser plane wave, an atom in a laser plane wave. When the atom absorbs the photon of the beam, it gains a momentum h bar k, because each photon has a momentum h bar k. When it falls back to the ground state by spontaneous emission, giving rise to fluorescence light, it loses some momentum. But because spontaneous emission can occur with equal probabilities in 2 opposite directions, the mean momentum loss is equal to 0 on the average. So after a cycle, the mean momentum change is h bar k. And the mean force, which is equal to the mean momentum gain per unit time, is just h bar k dn over dt, where dn over dt is the mean number of photons absorbed per unit time. That is to say, the mean, which is also equal to the mean number of photons spontaneously emitted per unit time. And this is dn over dt can be just written gamma sigma EE, where sigma EE is the probability for the atom to be in the upper state, population of the upper state, and gamma, the spontaneous emission rate, which is also equal to 1 over tau r, where tau r is the radiative lifetime of the upper state. At high intensity and for a 2-level atom, the atom spends half of its time in the upper state, which means that sigma EE is equal to 1/2. So the maximum value of the force is equal to h bar k gamma over 2, and the maximum value of the acceleration or the deceleration, E max, is just equal to F max divided by m. That is to say h bar k over m times 1 over 2 tau r. If we put orders of magnitude on this number, h bar k over m is just the recoil velocity of an atom just after the absorption of a single photon. That number is very small. It is 3 centimeters per second for sodium, 3 millimeters per second for cesium. Compared to the thermal velocity, which is a few hundred meters per second, that's a very small quantity. But tau r is only 16 nanoseconds for sodium. That means that you can repeat this process a large number of times. And when you divide h bar k over m by 2 tau r, you get something which is 10 to the 6 meters per second squared. That is to say 10 to the 5, the gravity acceleration, which is a huge deceleration. So that can be used to stop an atomic beam. You irradiate a laser beam by a counterpropagating laser, an atomic beam by a counterpropagating laser beam. If you start with an initial velocity of 1 kilometer per second, with such an acceleration, you have just to wait 1 millisecond for stopping the atom. And during this time, they travel over a distance which is 0.5 meter, which is not too big. So you can do the experiment in the lab. And the only problem you have to solve now is the fact that when the atom is decelerating, the Doppler effect is varying, and you have to adjust the resonance condition to maintain the laser on resonant. And this has been done by different methods. The first one, which was developed by Bill Phillips' group, was to change the resonance frequency of the atom by applying a space-dependent magnetic field, a Zeeman tuning. And the second one, which is still simpler, just by sharpening the laser frequency, which is now very easy when one uses laser diodes. Just for illustration, I show you some results we obtained in Paris on cesium by Christophe Salomon and Jean Dalibard, where here are plotted velocity distribution of an atomic beam, initially, which is the thermal velocity, and after slowing down ramp frequency scan, starting from here to here, and leading to a peak of slow atoms at 200 meters per second, or 145, 102, 60, 17, minus 8, minus 60. A negative velocity means that the atom has been stopped and go back in the opposite direction. So if you adjust yourself here between these 2 points, you can have the atom stop with a 0 average velocity. Now, that does not mean that these atoms have a 0 velocity. They have a 0 average velocity, but they have a dispersion of velocity around v equals 0. They have still a temperature. Now, I would like to discuss, is it possible to reduce this velocity spread? Is it possible to cool the atom? Because the temperature is related to the velocity spread. I will show you now, explain to you the simplest possible cooling mechanism, which is a laser Doppler cooling mechanism, which was introduced by Henge and Shallow for neutral atoms and by Wineland and Demet for free atoms, and which can be explained very simply. You take an atom moving with velocity v to the right and irradiated by 2 counter-propagating laser beams with the same frequency, the same intensity, the frequency being detuned to the red, omega L slightly smaller than omega A. If the atom is moving to the right, it gets closer to resonance with this beam because of the Doppler effect, farther from resonance with this beam. So the radiation pressure of this beam will be larger than this one. The 2 forces will not be balanced. You will get a total force which is opposite to the velocity of the atom and which for slow velocity is linear in velocity. So you will get a force minus alpha v, where alpha is the friction coefficient. And the friction coefficient is very strong, and the damping time is very short. And this is why the people from Bell Labs who observed first this cooling mechanism in 85 called the scheme optical molasses, because everything happened as the atom was moving in a pot of honey. Of course, you cannot go to 0 by such a scheme, because you remember that polarization can occur in a random direction. On the average, it's 0, but from one process to another, it varies in a random way, so that in momentum space, the revolution of the atom is a random walk. And exactly as in Brownian motion, you have a competition between 2 processes, laser cooling, which introduce the friction coefficient alpha, which I've just described, and momentum diffusion heating, which is due to the fluctuation of spontaneous emission and which can be described by a momentum diffusion coefficient D. You can calculate alpha and D and calculate theoretically the temperature, kBT Doppler, and find it is D over alpha. And you find easily that this temperature has a lower limit, which is h bar gamma over 2, that is to see h bar over 2 tau r, which is reached when the detuning is equal to half a line width, and which is equal to 240 microkelvin for sodium and 120 microkelvin for cesium. So it's already a very low temperature. But actually, I would like to make the following remark. If you look at the famous Einstein paper of 1917, you find that there is already a discussion of Doppler cooling in this paper because he was considering how atoms interacting with the blackbody radiation and exchanging linear momentum with this blackbody radiation because of the Doppler effect, we are able to reach thermal equilibrium. So I think one can say that the first discussion of laser cooling is contained in the 1917 Einstein paper. Finally, I would like to discuss the last example, which is the control of the position. Can you control the position of the atom? Can you trap the atom? Several traps have been proposed. I would like to discuss one of them, which has been proposed by my young colleague Jean Dalibard in 1986, which is called the Magneto-optical trap. And I explained the simple case of a G equals 0 to G equals 1 transition. Atoms are put in a magnetic field gradient along the z-axis. So the magnetic field varies linearly with z. The ground state, which is the m equals 0 state, is position as an energy which is position independent, whereas the two states, E plus 1 and E minus 1, have an energy which varies linearly with z. And suppose that you excite these atoms with two counter-propagating laser beams, sigma plus and sigma minus, having a frequency omega L slightly smaller than the atomic frequency omega A. What happens? Look at an atom which is going like that way. When it arrives here, at this point, Z1, the frequency of the G0 E plus 1 transition, that is the sigma plus transition, is resonant for the laser beam coming from this direction. So these atoms undergoes a radiation pressure from this beam, and it turns to the right. It is repelled to the right. When it arrives here, it becomes resonant with the sigma minus wave, and it is repelled to the left. And you see that the atom is bouncing back and forth between Z1 and Z2. Its motion is limited between two values. It is trapped. And in addition, you have a combination of trapping and cooling, and these traps are very convenient because they work not only at one dimension, as I've explained here, but also at 3 dimensions, and also they work in a cell, not for a beam, but for a cell. And they are deep, they are temperature, a depth of the order of 1 degree Kelvin. And shortly after the proposal, such a trap has been achieved by a collaboration between Dave Pritchard and Steve Chu. Let me give you an example of such a trap, which we have now in Paris. That bright spot you see here is the light which is emitted by a cloud of metastable helium atoms, which have been slowed down by the magnetic tuning method and which has trapped in a magneto-optical trap. And you look here at the fluorescent light emitted by these trapped atoms. The scheme also works in a cell, and here you have a Pyrex cell of 10 centimeter diameter. The atoms are in the cell, and the bright spot, yellow spot you see here at this point, is a cloud of cold cesium atoms which are trapped in the cell. So you can have now in a cell cold and trapped atoms. Now I'm going quickly to the second step of my talk, which is advances in laser cooling. Around the 88, more precise measurements were done on the temperature of these cooled atoms, which is not very easy to measure the temperature of cold atoms. And these experiments were initiated by the Gettysburg group, and the big surprise was the temperature was much lower than expected. Usually when you do experiments, you find results which are worse than the theoretical prediction. Here it was a very good surprise. The experimental results were much, much better than the theoretical result, and this quite surprising result was confirmed in Paris and Stanford. Let me first explain to you how the temperature is measured. The idea is very simple. You start with a molasses, which is a ball of cold atoms, like that. And at time t equals 0, you switch off all the laser beam. So the atoms are no longer moving in a viscous medium. They fly. They form a shower. And you look at the light they emit when they cross a laser beam which is located 7 centimeters below. And you measure the time of flight. And this time of flight is determined by gravity. It's determined by the initial position distribution that you can measure by a camera. You can also, that has been done, cut a slice in the molasses by pushing all atoms except in the shadow of a needle. So you have a very thin slice of cold atoms falling back so that you reduce the uncertainty due to the position distribution. And of course, the time of flight depends on the velocity distribution, which is the parameter you are interested in, that's the temperature. And if you fit the experimental signal, which is here, which is a very good signal to noise, with a theoretical fit comparison here, you find that the temperature is 2.5 microkelvin plus or minus 0.6, which I think is the coldest 3D kinetic temperature ever measured. So you have a very cold temperature. Remember that the minimum temperature predicted for Doppler cooling is 120. So what is the explanation? The explanation is you have sodium atoms are not two-level atoms. They have several Zeeman sublevels. You have optical pumping between these Zeeman sublevels. At low intensity, this optical pumping takes a long time. So you have long time in the problem, in addition to the lifetime of the excited state, which is short. And long times mean large non-adiabatic effect, large friction mechanism. That's the general idea. And I would like now to explain to you a more specific mechanism, a specific example, which we have developed in Paris with Jean Dalibard and which we have called Sisyphus cooling. And I would like to explain it to you on a simple case of the 1D molasses. Suppose that you take a 1D molasses, you take two counter-propagating laser beams. But now, because the atoms are not two-level atoms, we have to worry about the polarization. And I will take a configuration leading to a polarization gradient. And that's easy. I take two orthogonal polarization, linear polarization, for this beam and for this beam. Two orthogonal linear polarization. At a given place, these two laser electric fields will be in quadrature, giving rise to a sigma plus light. If you move lambda over 8 to the right, the two fields will be in phase. And the polarization will be linear at 45 degrees. If you still move lambda over 8, there will be again in quadrature, but with a minus pi over 2 phase shift instead of a plus pi over 2. So there will be sigma minus. And if you move again, you will have a linear polarization and then a sigma plus. So you see that in general, in a molasses where the polarization change are different, you have a strong polarization gradient over distances of the order of the wavelength. Let me suppose now that the atoms which are cooled have two Zeeman sublevels in the ground state, G minus 1/2 and G plus 1/2. And let me suppose that the excited state has a G equals 3/2 angular momentum. So we have four Zeeman sublevels in the upper state. E minus 3/2, E minus 1/2, E plus 1/2, E minus 1/2. And suppose that you are in a place where the polarization is sigma plus. If the polarization is sigma plus, you see easily that you have optical pumping, taking atoms from G minus 1/2 and putting them in G plus 1/2. So all atoms will be optically pumped in G plus 1/2. You see also that since the laser frequency is smaller than the atomic frequency, the two levels will be light shifted down. And because the square of this Glass-Gordon is 3 times smaller than the square of this Glass-Gordon, this light shift will be 3 times smaller than this one. So the two Zeeman sublevels will no longer be degenerate. They will be separated by a splitting which I call U naught, and which is the light shift. Okay? And all atomic population will be in G plus 1/2. Now, if I go to another place where the polarization is sigma minus, the conclusions are reversed. All atoms will be optically pumped in G minus 1/2, and the G minus 1/2 sublevels will be shifted 3 times more than the G plus 1/2 sublevels. So you see that the 2 sublevels are shifted like that, and when you move, they are shifted in the opposite way and again in the opposite way. So you see easily that the light shift of the Riemann sublevels oscillate in space like that, with the separation here, which is lambda over 4. That's the G plus 1/2 level. That's the G minus 1/2 level. They oscillate with an amplitude U naught. And you see that also optical pumping rates oscillate, because at this point, optical pumping tends to put atoms in G plus 1/2. At this point, it tends to put atoms in G minus 1/2. So you see that both light shifts and optical pumping rates are modulated spatially. But the important point is that these 2 modulations are correlated. There is a strong correlation between the spatial modulation of light shifts and the spatial modulation of optical pumping rate. And the correlation results in the fact that atoms tend to be optically pumped from the highest sublevel to the lowest one. So if you now take a moving atom, and if you suppose that the moving atom starts from the valley, has been just pumped here, it starts from the valley of a potential curve here in G plus 1/2. It moves to the right. It climbs the potential hill. It reaches the top of the potential hill where it has the maximum probability to be optically pumped in the other sublevel, that is to say, to the bottom of the valley, and so on. And you see that because of this correlation between light shift and optical pumping rate, you achieve a situation where the atom is always climbing, as Sisyphus in the Greek mythology. This is why we call this cooling mechanism the Sisyphus cooling mechanism, because it's exactly an atomic realization of the Sisyphus myth. And you see that during the climbing, the kinetic energy is reduced to the benefit of the potential energy, and the gain of potential energy is then dissipated by the optical photon, which is emitted, because the emitted photon has an energy which is larger than the absorbed photon. So the potential energy is dissipated by spontaneous emission, and so on. And you see that at each step, you decrease the total energy by an amount U naught, and the total energy of the atom decreases until the energy of the atom reaches a value corresponding to U naught, and then the atom is trapped. So you expect that the temperature obtained in this way should be kBT of the order of U naught. That is to say, you remember the light shift is omega 1 squared divided by delta, proportional to the laser intensity IL, and inversely proportional to the detuning. So that's nice. When you decrease the intensity of the light, you decrease the temperature. Could you go to 0 and get a 0 temperature? Of course not. Because the gain, the loss of potential energy after each cycle, which is of the order of U naught, if you want to have a cooling, the loss of potential energy must be larger than the gain of kinetic energy to the recoil. Because when the atom spontaneously emits a photon, it recoils. So it has a kinetic energy at least h bar square k square over 2m. And you see that if U naught is too small, if U naught is smaller than the recoil, you can no longer use this mechanism for cooling. But you see that now, that this mechanism leads to temperature which scale as a recoil energy and not as h bar gamma. And of course, it has been possible to make a complete theory of this cooling scheme with Yvan Cassin and Jean Dalibard, and one predicts that there is a universal curve giving p squared average divided by in unit of h bar square k squared versus U naught, the light shift, divided by ER, the recoil energy. And we predict that you must have a straight line, and that's a very good agreement with experimental results. You get here a plot of temperature measured versus the light shift in unit of gamma. And you see that the temperature is really a linear function of the light shift. And the different points correspond to different values of the detuning, which can vary by a factor 20. So we have really checked that that depends only on this parameter, omega 1 square over delta. And when the intensity is too small, then the curve starts again to increase. One interesting thing about this scheme is that the lowest temperature which can achieve correspond to values of the parameter where the oscillation frequency of the atom in the bottom of the potential wells is, the oscillation frequency is larger than the damping rate due to optical pumping. The oscillation period is smaller than the optical pumping time. You are in a new situation in this kind of problem where the characteristic time of the external motion are shorter than the characteristic time of the internal motion. And quantum mechanically, this means that in the potential well, which is here at the bottom is nearly parabolic, you have discrete energy levels, and omega oscillation large compared to 1 over tau p mean that the splitting between these energy levels is larger than the width of this level due to the rate of absorption. This means that we have a quantization of atomic motion in the light potential associated with the laser beam. And just a few weeks ago, we have observed such effect. We have observed by an experiment, I just described you briefly. We have submitted a letter where we have measured in a 1D molas, which is in blue here, we have measured the absorption spectrum of a probe beam in red here, and we have measured the absorption of the weak probe beam versus its frequency omega probe, and we have observed a curve like that, a gain, an absorption, two curves like that. And these two segments, we interpret them as Raman processes. This one, for example, we have discrete levels here. This level is more populated than this one. So we have processes where the atom in this vibrational level can absorb a probe photon and make a stimulated emission of a molas photon and go to the vehicle 1 level. And that leads to an absorption of the probe beam. We have an absorption of the probe beam at the high frequency part. This is omega for omega p larger than omega. And this splitting is just the oscillation frequency. And you have also other processes where you have first an absorption of the probe beam, of the molas beam, and stimulated emission of a probe beam, which lead to an amplification of the probe in the low frequency part, and this is what you observe. And by measuring this splitting, we can measure that I think is the first experimental determination of the oscillation frequency of the atom in the potential well. And it's nice that also similar results have been obtained by quite a different method by looking at the fluorescence light by Bill Phillips group in Gatesburg. So we think now we have a complete experimental evidence for the existence of this potential well and for the quantization of the atomic motion in this potential well. I would like now to give you have seen that you cannot go below the recoil. Actually, there are another scheme which we have developed in Paris, and that's the last part I would like to discuss now, the cooling below the recoil limit, which has been done with collaboration with Aspe, Arimondo, Kaiser, Van Stenkis. If you are interested in all these problems, you can look at the review paper we have written with Bill Phillips for Physics Today in October 90. Let me explain briefly what the subrecoil cooling mechanism is. It's actually a combination of two effects. A velocity selective coherent population trapping, which selects a group of atoms in a given state, in a given velocity state, and prevents these atoms from absorbing light by quantum interference effect of the same type I've described at the beginning of my lecture. And second point, optical pumping in velocity space, which accumulate atoms in this dark state. We have used for doing this calculation and this experiment transition 1 to 1, G equal 1 to G equal 1. You see here the 6 Zeeman sublevels, the 3 in the upper state, the 3 in the lower state. And the important point is that this Claude Gordon coefficient is equal to 0. So if you start with atoms which are equally distributed here, here, and here, if you excite this atom with two counterpropagating beams, sigma plus and sigma minus, they are optically pumped here and here. And from these two levels, if they absorb again a sigma minus photon, they can never come back to G naught because this Claude-Gordon coefficient is equal to 0. So after a few optical pumping cycles, the atoms are just moving, circulating between these three states. And we have a pure system called lambda configuration because we have a pure system of two sublevels in the ground state and one sublevel in the excited state. And now we can have nice interference effect because suppose that now, since I will show you that these cooling schemes leads to temperature which are smaller than the recoil temperature, now the de Broglie wavelength becomes larger than the laser wavelength, and we have to specify quantum numbers, not only for the internal state, but also for the atomic motion state. Let me call E naught P a state where the atom is in the upper state E naught with the momentum P along Z. And let me consider the state G minus P minus H bar K. In the atom in G minus with the momentum P minus H bar K. Because of angular momentum conservation, for going from G minus to E naught, you have to absorb a sigma plus photon. Since the sigma plus photon is coming that way, when the atom absorbs the sigma plus photon, it gains a momentum H bar K. So going from P minus H bar K and absorbing plus H bar K, it goes to E0P. So the two states which are coupled by sigma plus are G minus P minus H bar K and E0P. The same argument shows that for going from G plus to E0P, you have to start from G plus P plus H bar K, because now you have to absorb a sigma minus photon, which carries the momentum H minus H bar K. So you have to start from P plus H bar K in order to get to P. So these two states are coupled to this one by sigma plus and by sigma minus. And these two numbers are the two Claude-Gordon coefficients. So if I take a state which is a linear combination of these two states with a plus sign here, 1 over square root of G minus P minus H bar K plus G plus P plus H bar K, you see that the amplitude of absorption of sigma plus is equal to 1 over square root of 2. The amplitude of absorption of sigma minus is minus 1 over square root of 2. And the two absorption amplitudes interfere destructively. We are exactly in the situation I've described before. Such a state is not coupled by the laser light. Psi, this is why I call it Psi NC, Psi non-coupled. The matrix element of the laser atom interaction Hamiltonian between Psi NCP and E0P is equal to 0. Of course, if you take the minus sign, you take the orthogonal linear combination, now you have to add 1 over square root of 2 minus minus plus 1 over square root of 2. The two amplitudes interfere constructively, and this state is coupled. Okay, so you have a non-coupled state. Now, how can you select one non-coupled state from the other one? Now, this state is a linear superposition of two states. Have they the same energy? If I suppose that the magnetic field is equal to 0, the two Zeeman energies of G minus and G plus are equal to 0. But now you have to include in the Hamiltonian the kinetic energy Hamiltonian, P squared divided by 2m. And the kinetic energy of this state is P minus H bar K squared divided by 2m. And the kinetic energy of this state is P plus H bar K squared divided by 2m. And you see that the two kinetic energy are the same only if P is equal to 0. Because these two numbers are equal only if P equals to 0. So there is only one state which is stationary, which does not evolve in time because it's a superposition of two states with the same energy, is the state P equals 0. This is the velocity selection. As soon as P is not equal to 0, the two states have not the same energy, the phase factor appearing in the evolution exponential are not the same, and in other words, the kinetic energy Hamiltonian coupled the non-coupled state to the coupled state with the matrix element which is proportional to H bar K P over m. So we have now everything because we can now explain how things proceed. An atom in the non-coupled state P and Cp with P different from 0 can absorb light and go to the upper state. Then it makes a spontaneous emission. But spontaneous emission produces a random change of momentum because the spontaneous emission photon can be emitted in any direction. So after a fluorescence cycle, the change of momentum makes that the atoms can fall back in a state, in ground state, which has a non-zero overlap with a state C and Cp prime, with P prime smaller than P, and so on. So you see that you can progress towards P equals to 0, and you see that the smaller P, the longer the time spent in CNC of P, because the smaller will be the coupling between CNC and P and CC of P introduced by the kinetic energy Hamiltonian. So the longer the interaction time T, theta, the smaller the range delta P around P equals 0, or value of P, for the state CNC of P with P smaller than delta P, in which the atom can remain trapped during the interaction time. So you see that by that scheme, you can accumulate the atom in a small velocity interval, which decreases when you increase the interaction time. So there is no limit to the temperature which can be obtained by such a scheme. And you see that the atom will pile up in a double momentum state, CNC of P, with P smaller than delta P, and delta P decreasing. You can show that delta P decreases as 1 over square root of theta. We have observed actually this effect by letting an atomic beam of helium crossing 2 sigma plus and sigma minus counter-propagating laser beam, and by analyzing the momentum distribution of the atom after the interaction zone. And that's the result we obtain. That's the momentum distribution of the atom before the interaction zone. That's the distribution after the interaction zone. And you see that we get 2 peaks because the atom is in a double momentum state. So the probability to measure, to find the value of P is either P minus H bar K or P plus H bar K with P smaller than plus or minus delta P. And the fact that you reach a sub-recoil cooling temperature is revealed by the fact that the width of these 2 peaks is smaller than the splitting 2 H bar K between them. Actually, in this experiment, we reach a temperature of 2 microkelvin, whereas the recoil temperature is 4 microkelvin. That means that the de Broglie wavelength is 1.4 microkelvin, whereas the laser wavelength, which was used to do the cooling, was 0.08 microkelvin. We did this experiment with 4 years ago with a thermal beam having a velocity of 1 kilometer per second. Now we have a cloud of stopped atoms. We are planning to, these atoms are very slow. We are planning to leave them fall and cross a 2D configuration of laser beam and produce a dark state, 2-dimensional dark state, which we hope within a few months could give us the possibility to reach the nanokelvin range in the temperature. I would like to briefly end my talk by giving you 2 applications of this scheme of cold atoms, now the last part of my talk. The first one is the so-called Zacharias atomic fountain. Up to now, 2 such fountains have been achieved, one in Stanford on sodium and one in Paris in cesium. The idea is that to have a very good atomic clocks, we must have a long interaction time. Usually atomic clocks are done with atomic beams, with 100 meters per second atoms. Now we have atom at rest. We have a much longer interaction time. In our experiment, the velocity of the cesium atoms is only 2 centimeters per second. So what we can do, we can take atoms, and we can throw them like that, during having them passing through a cavity, once in the up direction and one in the down direction. And when they pass it in the cavity twice, you get 2 pulses. They experience 2 pulses of microwave, and we can observe Ramsey fringes. And the time between the 2 pulses is of the order of 0.3 seconds, to be compared with the 1 to 10 millisecond time of flight achieved in the best atomic clocks with thermal atoms. So we can hope to gain 2 or 3 orders of magnitude with respect to the width of the cesium clock transition. How to launch the atom? Of course, the simple thing would be to apply radiation pressure in that direction. But here we heat the atom by momentum diffusion. So a most clever scheme is to use, for the two vertical beam of the molasses, two different frequencies, omega minus delta omega and omega plus delta omega, so that when you go to the moving frame, such that V equals delta omega over K, because of the Doppler effect, in the moving frame, the two beams will have the same apparent frequency, so you will have a moving molasses. And the atom will be locked to this moving molasses, so they will move while remaining cooled. So we can launch the atom while keeping them cold, keeping the same temperature. That's an example of the detail of the experimental setup. We have here about 5 centimeters, because in our experiment, the vacuum was such that we couldn't send the atom at a distance higher than 5 centimeters above the cavity. But anyway, that's an example of Ramsey fringes which are obtained. And the important point is that the central fringe has only 2.03 hertz to be compared with a few hundred hertz of the atomic clocks, the current atomic clocks. So you see, we have already, as far as the width is concerned, at nearly 2 orders of magnitude improvement in the precision of the clock. The second example concerns the fact that when you go to low velocity, to cold atom you have low velocity. Low velocity means that you have long Debye wavelength. And now there is a new field which is starting in physics, which is the wave aspect of atomic motion. Atomic motion appears, you have to consider the atom now as a wave, not only as a particle, but as a wave. And there's new fields which are emerging, which are called atomic interferometry, atomic optics, and which are studied extensively in different labs, including Dave Pritchard lab here, Minek lab in Constance, and Steve Chu in Stanford. And in Paris, we are devising an experiment using what we call a gravitational cavity. We would like to make, we start with a parabolic mirror, like that, and we form at the surface of the parabolic mirror an evanescent wave, which is detuned to the blue. The laser frequency is larger than the atomic frequency. So the light shift is positive. Since the light shift is positive and decrease exponentially with the distance, we have a potential barrier when you approach the surface of the mirror, which increases exponentially. And if the initial velocity of the atom is smaller than the height of the barrier, the atom will be reflected. Of course, that experiment has been done already by two groups, and in particular by using a grazing incidence, because if you use the thermal beam, the velocity is large. You have to use a very small angle so that the velocity along this direction is small. But now we have slow atoms. We can just let them drop on the surface. We have a molasse, or a magneto-optical trap, and we release the beam, and the atom fall. And they fall like that as a trampolino. And because such an effect has been already observed by at least 2 people, but since the first experiment we are using a plane mirror, and then the atoms are leaving the illuminated zone, if you are using a parabolic mirror, then the atoms are trapped also in the transverse direction, and you can get a stable motion. And actually, you can solve Schrödinger equation exactly when you take the gravitational field and the boundary condition, which is a parabola, that can be solved exactly. And that's, for example, an example of quantum mechanical solution of Schrödinger equation, what we call a quantum mechanical mode. And we hope to be able to observe such modes, and we hope to be able to put more than one atom in a given mode. Because if we are able to put more than one atom in a given mode, then because of the Bose effect, Bose factor, if there are n atoms in a mode, a further atom will like to join with the probability n plus 1 instead of the other modes which are unoccupied. So we'll have a tendency of atom to cluster in already occupied modes. That would not be Bose condensation. That would be another simpler manifestation of the Bose factor. I will stop here, and I would like now to conclude. I hope to have convinced you by comparing the first part of my talk and the second part of my talk that there are new physical mechanisms using old well-known effects, such as optical pumping, light shift, coherent population trapping, Handler effect, etc., which allow one now to cool atoms down to 1 microkelvin and to reach de Broglie wavelengths larger than the laser wavelength. I think that this result provides a great stimulation for investigating the application of cold atoms in various domains of physics, such as atomic clock, atomic frequency standard, atomic interferometry, atom optics, and also for a great stimulation for trying to get a still better understanding of the atom-photon interaction. We are now, I hope to have convinced you that the fact that the atomic motion is quantized prevents us now from thinking of an atom as a point. We have to consider it not only as a point, but also as a wave. And we have to solve Schrödinger equation for the center of mass motion. Among the present development, the theoretical development, one which seems very promising, is a development that's called quantum Monte Carlo approach, which try to apply to this kind of problem, quantum Monte Carlo simulation, which preserve the quantum features of the problem and which would be extremely useful for understanding what happened not only in 1D, which I've mostly explained today, but also at 2 and 3D, which correspond to real experiments. Finally, I would like to acknowledge my colleagues in Paris who have done all this work. In the Paris group, there are 4 permanent people in addition to me. Alain Aspect, who was with me since 1984 and who left last October to Institut d'Optique. He got a new position there, and I think you have heard of his lab lecture a few weeks ago. He has been replaced by Karl Arminov, coming from Helsinki. There are 2 other permanent people from CNRS, Jean Dalibard and Christophe Salomon. These 4 people, Robin Kaiser, Nathalie Vonstensky, Delphine Grison, Yvan Cassin have already finished their thesis, and they left the lab. I hope that Yvan Cassin could come back. Olivier Emile, François Bardot, Brahim Lounis, Pierre Desbiol, and Philippe Bouillet are doing their PhD. And we have benefited from the various visitors in the lab during the last few years. I mentioned here only a few visitors who spent at least 6 months: Hal Metcalf, Bill Phillips, Ike Silvera, Ennio Arimondo, Chris Guert, Chris Westbrook, and also 2 other people from France, André Cléron and Sadia Gelati. Thank you very much for your attention.
Thank you. Are you open to questions or comments? Ike, Ike.
In the gravitational cavity that you just spoke of, do you expect the atoms to lose energy by dissipation as they bounce off the surface and then settle right down to the bottom?
If the laser detune, if the laser frequency is detuned far to the blue, then the bouncing will be perfectly elastic. There will be no dissipation at all. That will be a pure potential reflection. The problem is that you have a small absorption probability, and we have to reduce it as much as possible, because once you have an absorption, a real absorption process, a scattering process, then first you have a momentum kick, which can, of course, take the atom away, and you have also a destruction of the spatial coherence length.
See, I was thinking if you could adjust the dissipation properly, then you could settle down into the bottom of the well and get Bose-Einstein condensation. But it might be a problem.
No. It depends what you are interested in. If you are interested in the wave aspect of atomic motion, we are interested to have long coherence lengths, and we have to avoid spontaneous emission, because spontaneous emission can be considered as a measurement process which destroys atomic coherence. So we have to avoid resonant processes, so we have to go far away from resonance. So that needs to have powerful laser. Of course, we can focus the laser as much as possible, but if the bright spot is too small, then the probability that the atom escape is large. So there is a trade-off between the intensity and how far you can detune. And we are planning to use in our experiment a Titan sapphire laser, so that we hope in the first step to be able to observe 50 bounds.
Dave.
Well, Claude, as an experimentalist, I feel maybe that there's kind of an end to an era, by which I mean that for 70 years or so, what we've been trying to do in atomic physics is to get greater control over atoms. So first there were atomic beams to isolate them from the rest of the world, and then resonance techniques to control the internal states and optical pumping. And now here we finally got the external motion quantized and basically under control. I mean, what is there to do now?
I think what we're now entering a new period where we should use these cold atoms to make new physics. One example is atomic interferometry. Obviously, atomic interferometry, if we can increase the surface of the interfering arms, that provides improvement factors which are really incredible with respect to light interferometry. Another exciting field is to this quantum statistical effect. What happens if you have more than one atom in a given quantum mechanical moment? So I think also collision process with cold atoms, we were discussing that a few hours later before, that also provides a lot of new things. So I think there are a lot of exciting development we can hopefully expect in the next few years. Also, I think the moral of this story is that to have a field progressing, we must control everything. Because, as I mentioned in my lecture in Washington, in the 1917 paper of Einstein, he was saying that one should pay the same attention to the conservation of linear momentum than to the conservation of energy, even if it is less spectacular. He was saying that at a time where nobody was considering momentum. And I think that, obviously, the whole field of laser cooling and trapping is a beautiful illustration of this sentence. And I think that the recent development in the field shows that one should also pay the same attention to angular momentum, because it's really angular momentum is clearly involved in this new mechanism. If the atom had no angular momentum state, we couldn't have the Sisyphus cooling, we couldn't have coherent population trapping. So I think we need everything. So I think it's important to have a control of all degrees of freedom if we want to make new exciting physics. Of course, it has been a lot of excitement to understand this mechanism, but I think now we have to go further.
Yeah. I just did want to mention that the lecture is being videotaped, so that your concern that the field has been exhausted and there may not be anything left to do has been recorded. If you have second thoughts on that, we might be able to remove it. It's just that actually this may be a good omen, because when an authority in the field says the field is finished, that's generally when things just open up afresh. Michael.
When you model this cavity for atoms with gravitation, how do you treat gravitational term in the Hamiltonian when atom is away,
No,
not a particle?
we just add to the Hamiltonian, to p squared over 2m, minus mgz. So it's a very simple Hamiltonian. P squared over 2m minus mgz. The only thing, we have a boundary condition, the wave function corresponds to parabola. And the problem is completely soluble in parabolic coordinates. And
It's not time yet to treat gravitation in a quantum way?
no, why? No, I think it's a potential energy which is minus mgz. That's all. No. In this problem. In that specific problem.
Same thing as applying an electric field.
Yes.
Yes.
Excuse me?
The mirror, the parabola, the surface.
Oh, it's by polishing. With the sphere, locally it's.
No, mean how do you make the surface cold? If the surface is very hot, then the atom boundary can.
No, but they don't touch the glass.
Oh.
They have, the glass is covered by a layer of light, and the atom is reflected by light before reaching. If the atom sticks the wall, we are lost. Of course, there is another interesting field which I have not mentioned here. What about collision of these cold atomic surfaces? That would be also a lot of open questions. But here, in this experiment, we are avoiding any contacts between the atom and the surface. We reflect the atom before it reaches the surface. You know, nobody has still been able to make a quantitative theory of what happened in a 3D molar. Complicated because you imagine easily that how complicated is the field polarization in space when you combine three standing waves. Some calculations have started to be done by Monte Carlo techniques. And I think that we have some equilibration between the temperature in the various directions. Some coupled, yeah. It is strange because we have a simple proportionality factor between the temperature at 3D and temperature at 1D, which seems that there are perhaps simple explanations which have to be found.
If you have more than one atom per node, does
Yes.
the interaction between them shift the resonance frequency and move
Yes,
away from the
sure. That's a big problem for trying to have, for example, in a magneto-optical trap to put many, many atoms. But here what is nice is we are not working with the lowest mode. We are not trying to put atoms in the lowest energy mode, where small mode. We are trying to put atoms in a large N mode, highly excited mode, where on the average the atoms are more distant than in the lower state. We are trying to do a laser mode with atoms, with the Broglie waves. You know, a laser mode in a cavity is a mode with N, which can be very high. We are trying to do the same thing, replacing optical waves by the Broglie waves. But what we would like to find, that's very exciting, a scheme for having the equivalent of a LEO filter, which selects one mode, which introduces loss for all modes except one, or a few. So we have to find the equivalent of a mode selector.
Okay.
I think.
One more question.
What are the practical limits for the cooling the temperature achieved by Sisyphus cooling?
You mean what is the prediction?
Yeah.
Yes.
In terms of practical, I mean, it seems to me as though three magnetic fields
Understood. Excuse me, I'm not understanding clearly your question. You want to?
Sisyphus cooling.
Yes.
Straight magnetic fields will be important.
Yes, sure.
What do you think is the practical limit to the temperature?
You have to control the magnetic field so that the magnetic shift is smaller than U naught, that's the light shift. But that's easy with shield or with compensating cores. But when you are compensating the magnetic field, we have a theoretical expression giving the lowest temperature which can be reached by Sisyphus cooling, and it's of the order of 3 or 4 PRMS, of the order 3 or 4 H bar K. So we get the minimum P, which is about 3 recoil momentum. That the minimum can be obtained by Sisyphus cooling. The other scheme, you can go as low as you want. But you have a state which is a linear superposition of states differing by their momentum and their internal state.
Okay. Well, Claude, we appreciate this talk. I actually somewhat share Dave's feelings because it looks like just about everything that can be done has been done. But I also believe myself when I say that this is still a beginning. In any case, we appreciate very much your explaining this work to us so beautifully and clearly.